Welcome everyone. Physical design is a crucial phase in a semiconductor chip design process where the logical representation of the chip is transformed into its physical layout. Physical design directly impacts a circuit's performance, area, reliability, power, and manufacturing yield. There are different stages in the physical design flow, such as partitioning, floor planning, placement, clock tree synthesis, routing, and timing enclosure. Various algorithms are proposed for each stage of the physical design. Today, we are going to study about one such algorithm used for routing. We, the students of RVCE, present you a role play of a maze routing algorithm. There are different kinds of maze routing algorithms, and we will be simulating the process of Lee's algorithm by routing paths through a chip layout resembling a maze.
So, let us dive into the maze routing adventure. Myself, Rorik, and I'll be your narrator for this entire process of routing. Allow me to introduce you to my group, which comprises of three core teams. First, we have the maze explorers. These individuals represent the routing algorithm. They explore different paths through the maze and are responsible for finding the routes from source to destination. So let me introduce you to the set of maze explorers. We have Vaibhavi R, who will be our maze explorer 1, Srinivas Anand Kamath as maze explorer 2, Nidhi R Singh as maze explorer 3, Manjunatha Gowda N as Maze Explorer 4 and Vaishnavi LG as Maze Explorer 5. The second core team is the team of coordinators. The Maze Explorers update the status of the path taken by them to the coordinator, and this person analyzes the explored routes to ensure they meet the specified criteria. We have Sudhanva VS stepping into the role of the maze coordinator. The third core team is the team of routers. These individuals are responsible to perform the actual routing, that is both horizontal and vertical routing between the source and the destination. We have Skanda V. Joyce as the vertical router and Sudip Kumar BS as the horizontal router. Moving on, the entire chip area is divided into small manageable squares that is called as grids. Imagine our chip as a grid of interconnected nodes with obstacles blocking certain paths. The source and the destination are the terminals that are to be connected. Our goal is to find optimal routes for our connections while avoiding these obstacles. We have considered a 6 cross 6 matrix, also termed as a maze, where S denotes the source and D denotes the destination. Our maze also contains some other elements such as congestions and blockages. Blockages in a maze can be due to the presence of standard cells, hard macros, keep out margins, etc. And congestion arises due to higher density of pins or cells in that particular grid, or due to the presence of different routing layers connecting other pins of the chip. So having our route between our desired source and the destination through this particular grid will create some issues such as crosstalk that will affect the signal integrity. Our task is to navigate this maze, finding optimal routes for our connections while circumventing obstacles and congestion. Buckle up as we dive deep into the world of electronic design automation. So this is the adaptation of the 6 cross 6 matrix which we have considered as an example. Here, the cross marks refer to the areas of congestion present in the matrix or the maze which we have considered. And the blockages are indicated by placing the backpacks in the corresponding grids. The source is denoted by the letter S and the destination is denoted by the letter D. The algorithm starts with the maze explorers ready to explore in all directions from the source to the destination. So the five maze explorers are at the source point ready to start their journey. Maze explorers 1, 3 and 5 are moving in vertical direction and maze explorers 2, 4 are moving in horizontal direction. At the first step, since there is no congestion or blockage, all the maze explorers move on to the next grid. This is marked as step 1 and it is updated to the maze coordinator. The coordinator labels the value of that particular grid as 1. During the second step, all the maze explorers face a congestion block in their respective directions. So moving in their respective directions will cause some signal integrity issues. So the maze explorers change their directions by indicating it to the maze coordinator. Maze explorers 1, 3 and 5 change their directions from vertical to horizontal and maze explorers 2 and 4 change their directions from horizontal to vertical. All the 5 maze explorers again intersect at a point in the next step and it is labeled as 2 by the maze coordinator. Further, all the 5 maze explorers continue their journey in the respective directions, that is, explorers 2 and 4 move in vertical direction, explorers 1, 3 and 5 move in horizontal direction as there are no congestions or blockages in their respective directions. These grids are labeled as 3 and 4 by the maze coordinator. After the fourth step, maze explorers 2 and 4 face a blockage ahead in their direction, whereas maze explorers 1, 3 and 5 have two possible paths, that is, to continue in their respective direction or to change from horizontal to vertical. Maze Explorer 5 changes her direction from vertical to horizontal, exploring a new path, whereas Maze Explorers 1 and 3 continue in their horizontal routing direction. Maze Explorers 2 and 4 change their direction from vertical to horizontal, and this is labeled as 5 by the maze coordinator. At the sixth step, Explorer 1 changes her direction from horizontal to vertical to explore a new path, whereas Explorer 3 continues in horizontal direction. Explorer 5 changes her direction from vertical to horizontal as she meets a dead end. Explorers 2 and 4 move in horizontal direction as there are no blockages in the upcoming grid. This is labeled as 6 by the coordinator. At the next step, Explorer 1 is surrounded by blockages, so she ends her exploration. Explorer 3 meets a dead end and is also surrounded by blockages, so she also ends her journey. Explorer 5 moves one step in the horizontal direction. Explorers 2 and 4 face blockage in the horizontal direction. As a result, they change their direction from horizontal to vertical. This is labeled as 7 by the coordinator. At the next step, explorers 1, 3 and 5 have all ended their exploration by meeting dead ends or blockages. Explorers 2 and 4 have two possible paths. One is to continue in vertical direction and one is to change to horizontal direction. So, Explorer 2 continues in vertical direction whereas Explorer 4 changes his direction to horizontal. This is marked as 8 by the coordinator. Further, Explorer 2 is surrounded by blockages. As a result, his journey comes to an end. Explorer 4 meets a dead end in the horizontal direction. As a result, he changes his direction from horizontal to vertical and reaches the destination. Out of the 5 maze explorers who started their journey in different directions from the source, only Maze Explorer 4 reached the destination. So, this path will be the optimal path for routing from the source to the destination. The maze explorers have successfully accomplished the mission for what they had been sent. That is, they had to find the optimal path from source to destination. Now, It is the role of the coordinator to highlight this path, that is, the path traced by the Maze Explorer 4, and indicate it to horizontal and vertical routers. In our demonstration, the coordinator starts from the source and traces the path traversed by Maze Explorer 4. He moves one grid at a time by naming each grid with a step number. So, the total number of steps taken to reach the destination is 9. Once the grids through which the routing has to be done is highlighted and is conveyed to the routers, the coordinator ends his operation. We have reached the final phase of the algorithm, that is, the phase of routing. Once the coordinator has highlighted the path to be routed, it is the role of horizontal and vertical routers to perform the actual routing between the two terminals. Generally, routing is done from the destination terminal to the source terminal. That is, the path highlighted by the coordinator is backtracked by the routers to perform routing. We are highlighting the routing layer through a black tape running from destination to the source. The first step is to connect the destination to the grid numbered 9 by vertical routing. Then, horizontal routing is performed between the grids labeled 9, 8, and 7. Once the horizontal routing is completed, again the routers perform vertical routing between the grids labeled 7 and 6. Later, horizontal routing is performed between grids numbered 6, 5, and 4. The vertical router then connects the grids 4, 3, 2, and 1. Finally, the horizontal router connects the grid labeled as 1 with the source, thereby completing the routing from source to destination. So this is how the leaf maze routing algorithm works.
Hi, myself Sandeep, and I would be summarizing the Lee's maze routing algorithm used in the field of VLSI design for automatic routing of interconnect. In the left hand side, we could see the initial phase of Lee's maze routing technique, and in the right hand side, we could see the final phase of Lee's maze routing technique. So this algorithm is a breadth first search algorithm that explores the maze of 6 cross 6 grid layout to find a path from source node to destination node while avoiding a blockages which are highlighted as a blue color and congestion which are highlighted as red color. Like as first stage of this particular lease maze routing is assigning a value for the source cell. So initially the source cell would be highlighted as the cell 0. Based on the first breadth search algorithm, the adjacent cells will be marked with the cell name as 1, where in the left hand side we could see a congestion which are highlighted in the red color. Henceforth, the algorithm tracebacks to the vertical direction where it can go up to cell count number 4. Up to cell count number 4, there are no blockages or congestion, but it detects a blockages is found. Hence, the search proceeds to the cell where it has no blockages and it completes the routing up to the destination. Overall, it takes 9 cell counts to reach from source to destination. The traceback starts from destination to source, which guarantees the breadth first algorithm the shortest path from destination to source if there are more than one or two possible tracks available. Hence, Lee's maze algorithm is effective in routing. Thank you.